So when it comes to balancing an equation, there are many ways to do it right. However, there's some underlying kind of cardinal rules of balancing equations that we have to stick with, and then after that, there's a little bit of room for creativity. The main thing, remember that we are balancing to observe the conservation of matter, and we must have the same number of each type of atom at the beginning and the end. Absolutely. So that is the point of balancing. That is why we do it. That is the goal we are trying to get to. We have to have the same number of each type of atom at the beginning and at the end. Coefficients and subscripts have to be whole numbers. We can't have half a molecule. We can't have half an atom. That would break our reaction. We also cannot change subscripts. Okay, we can only change coefficients. Hopefully, we're going to get to the point where you all can kind of predict those subscripts and predict what molecules are going to be being made. However, especially starting out here, those little numbers we can't change. So it's really important that the only thing we are changing is the number in front, which is our coefficient. All right. So first step is to balance an equation is just figure out if it's balanced or unbalanced already. The nice thing is a lot of times, or at least some of the time, you're going to look at it and say, oh, that's already actually balanced. I don't have to do anything, which is kind of nice. So let's try these examples here. If I look at tin oxide, I have 1 tin in my reactant. I have 1 tin in my product. I have 2 oxygens in my reactant. I have 1, oh, not balanced, right? I can already tell as soon as we have one that's not equal on either side, we know that we're going to need to do something to balance it. All right, let's look at this one. In this case, I have, 2 hydrogen molecules, and each hydrogen molecule has 2 hydrogen atoms. So 2 times 2 is 4. I have 4 hydrogen atoms in my reactant, and I have 2 times 2, 4 hydrogen atoms in my product. All right, so hydrogen's all right. I have 2 oxygen atoms in my reactant, and I have 2 times 1 oxygen, so that is 2 oxygen atoms in my product. So 4 hydrogens, 2 oxygens, 2 oxygens, we're good to go. Great. So the second one is balanced. Let's look at the last one. N2 plus H2 produces NH3. So this is a synthesis where I have these two things coming together to make one. I've got 2 nitrogens on this side. I've got 1 nitrogen on this side. So I can already tell this is not balanced. We're going to need to balance it. So first step, recognizing whether it's balanced or unbalanced. And that just involves counting our atoms on either side. If we look at this one, we've got 2 irons on the reactant side, 3 oxygens on the reactant side, and 1 carbon on the reactant side. On the product side, I only have 1 iron, so again, can already tell that this is not balanced. This is the one that I just did a moment ago, where hydrogen gas and oxygen are being put together. The 2 gases are being put together, and when the 2 are put together in the right conditions, we're producing water, and this one is balanced. Great. So first step, figure out if it is balanced already. Okay, so that's step 1. Talked through a couple examples, and now we're going to go on to step 2 and step 3. So step 2, if you have an unbalanced equation that you need to balance, is make a table. All right, make a table to count and just have a record of how many atoms you have on either side of the equation. And then number 3, and this is how I like to phrase it, number 3 is pull the thread. All right, look at your table and identify one of the things that is not right? One of the things that doesn't match. Add a coefficient to make it balanced. Update the table. When you update the table, it's going to change the thing you wanted to change, and a lot of times it's also going to change something else, okay? And at that point, this is where the thread part comes in. Whatever the unintended change was, stick with that and keep going until both sides are balanced. Again, though, there are multiple ways to do it right. And so this is just how I like to phrase it. So this is shamelessly stolen from a coworker, Miss Ruckflynn last year found this, and it was just a wonderful slide. So I wanted to put it in so we could check it out here. So we have this picture here starting out where we've got N2 and H2 producing NH3. And this is the table. All right, we've got reactants, we've got products. We're going to go ahead and put in all the types of atoms we have on the side. So when you make your table, reactants and products at the top every time, and then on the side you're going to say this is how many nitrogens I have, this is how many hydrogens I have. If you had other atoms, you'd put them in there as well. Let's go ahead and fill it in with the tally at the beginning. I have 2 nitrogens and 2 hydrogens. 2 nitrogens and 2 hydrogens in my reactant. I have 1 nitrogen and 3 hydrogens in my product. Cool. Well, I can see these are not equal. These are not equal. And this is where kind of style stuff comes in of where you like to start. I never start with hydrogen or oxygen because a lot of times those are in multiple molecules on both sides, and it makes it hard to count. So a lot of times I like to start with pretty much anything else that is broken, that is not equal, rather than hydrogen or oxygen. So let's go ahead and start with nitrogen. If I put a 2 here, a 2 coefficient in front of that ammonia molecule, when I do that, that's going to update the nitrogen to 2, right? But it's also going to change the hydrogen. So I have to update that as well. The coefficient in front is representing the fact that you have, however many it says of the molecule as a whole. You have to double, in this case, both things in the molecule, not just the thing that you wanted to double. Both are, it's a package deal. All right. Well, we're still on a good track here because nitrogen is balanced now, and the hydrogen isn't. So this is the only thing left to balance. Now I'm going to come over and see what I can do to the hydrogen here to increase it so that the hydrogen on the reactant side and the hydrogen on the product side is the same. Put a 3 in front of that hydrogen gas, and what do you know? 3 times 2 is 6. Now I have the same number of nitrogens and the same number of hydrogens at the end of the balancing process. So let's go ahead and try that here with another example. First, we want to see, is it balanced or unbalanced? Well, if I look, I've got 1 carbon on the reactant side, 1 carbon on the product side. That's fine. I've got 4 hydrogens on the reactant side. I've got 2. It isn't balanced, so we're going to have to fix that. So I'm going to go ahead and make my table. Every time reactants and products go on the side, every time those elements that are involved go on the left side here. So I have 4 hydrogens, I have 2 hydrogen products, I have 2 oxygen reactants, and I have 3 oxygens in the product. Don't know if that's bugging anyone else, but we're going to fix it real quick. Alright, so we can see these are obviously not balanced. Well, I know a minute ago I said that I prefer, whenever possible, to avoid starting with hydrogen and oxygen. But this time around, just not going to work. Those are the only 2 things that aren't balanced, so we're going to have to start with one of them. Let's go ahead and start with the hydrogens. Cool. I need to bring this up, so I'm going to go find my hydrogens in the product. Okay. I can see that if I put a 2 here, that's going to bump that up to 4. And because it never does just one thing, it's going to affect the molecule as a whole. I have 4 hydrogen atoms, and I now have 2 oxygens here. The 2 oxygens here plus the 2 oxygens from that make it up to 4. All right, so my number there went from 3 to 4. Well, good. Hydrogen's balanced. Now I just need to balance this one. Okay, well, let's go find the oxygen in the reactant. It's right there. All right, if I put a 2 in front, then 2 times 2, I now have 4 oxygen. Everything is tidy and happy and great because they are balanced. We are good, right? I need For my chemical equation, I'm going to have 1 methane and 2 oxygen molecules. So methane gas and oxygen gas. I put the two together in a combustion, and what do you know? I made carbon dioxide and 2 molecules of water, as well as some energy, which is not written there. So that is how that would work. Kind of interesting, kind of cool. All right. And here is the completed one. When I do this on paper, I do like to cross out my number and write the updated number with the coefficient. Just to kind of keep a record of what did I start with, where are we going. So like I said, there are many ways to balance equations correctly. There are a couple important notes I want to throw out there. I recommend don't start with hydrogen or oxygen if you can avoid it. Generally, leaving them for last is easier because they'll be in multiple things. So if I go back to that previous example, you'll see how in the product, the oxygen atoms are both in carbon dioxide and in water. That is actually what made me choose to do hydrogen first. So whenever I can avoid starting with something that's in multiple molecules on one side, I do that. Whenever you have an ionic bond, check to see if there's a polyatomic ion in it and count that as a unit. The polyatomic ions, I'll pull up here again in a moment and just kind of show them off on the side. You don't have to do this, but it does make it a lot easier because you're not having to do, 3 times 4 times 2. You can just say, oh, I have 2 of that group, rather than counting individual atoms, which will make more sense with an example. And lastly, if you see an atom that is in multiple reactants or multiple products, leave them until the end. So revisiting that example, oxygen's in multiple places in this example, so that's how I decided to leave it towards the end. Last thing I want to check in about is the conservation of matter is really the conservation of mass. This is how it was figured out and established a very long time ago. What I want to point out, this is a balanced equation, okay? And the deal is, if you look at the mass, and we go back to atomic mass, if I have 2 nitrogens, okay, and I have 6 hydrogens, so 3 diatomic hydrogens, 3 diatomic hydrogens. So I have 6 hydrogens, so 2 nitrogens and 6 hydrogens. The mass is 34.062. All right, so I've got, this is the mass of my reactant side. And if I look at the product side and I say, oh, okay, well, I have 2 nitrogens and I have 6 hydrogens, right? I have 2 times the mass of nitrogen plus 6 times the mass of hydrogen. When I do that, it looks very similar because it's the same thing, right? Like the conservation of matter is the conservation of mass. And if we run a chemical reaction, we should not have a change in mass as long as we keep the system closed, right? If we make a gas and some of the matter leaves the system because it bubbles away, right? It didn't disappear. It was still made into the gas, and we can capture the gas and measure the gas, and it'll still all add up. But the conservation of matter is the conservation of mass. We can use atomic mass and our balanced equation to demonstrate that relationship between the two. Last thing I want to talk about here, there are a million right ways to balance a chemical equation, really. There are loads of good videos out there about how to do it. These are the tips that work the best for me, and where I like to start, but these are all other videos that I found that were really solid videos that you're welcome to check out. So we're going to be working on a packet today. When you're done with the packet, you're going to come up and, well, first you're going to show me your notes. I'm going to give you the packet. Once you finish with the packet, let me know so that I can give you your homework sheet. The goal today is to be identifying whether it's balanced or unbalanced. We're going to be doing, like I said, lots of practice problems with this, and it's going to show up pretty much every day for the rest of the unit. Don't let it freak you out if it's making you nervous at all. I hope it doesn't. We're going to do some practice. Y'all are going to be excellent at it soon. Fingers crossed. Thanks.